In this video, I'm going to show basic PyTorch. Okay, so this is how you create a torch tensor with a range of 5. If you remember regular Python, when you put range, it would start at 0 and then go up to, but not including 5. You know, like stop signs, you go before the stop sign to stop, or people do. So 5 is like the stop sign, so it ends at 4. So it starts at 0, 1, 2, 3, 4. That's 5 things, because it starts at 0. So this is 0 through 4, and this is 0 through 4. And this is just as if you were multiplying two individual numbers in regular Python. Just put the time symbol between, and it'll multiply element-wise. So it'll take the 0 times the 0, and hold on, I'll clarify it real quick. Okay, so this is what it looks like. So I'm going to copy this, paste it up here. So that's what each of these looks like, 0, 1, 2, 3, 4. All right, so I'll paste this here too. All right, now if I do times, okay, I can say 0 times 0. This is what element-wise multiplication is. 0 times 0 is 0, comma. Then 1 times 1 is 1, comma. 2 times 2 is 4. 3 times 3 is 9. And 4 times 4 is 16. Okay, so this would say that element-wise multiplication of this with this is equal to this, 0, 1, 4, 9, 16. Now, if I go down here and do A times B element-wise, and, oh wait, hold on, syntax error, just a second. There. Now if I run it, there. So 0, 1, 4, 9, 16, and that matches with this, 0, 1, 4, 9, 16. So that's how you do the element-wise multiplication. Element-wise addition, it's the same pattern. It's just, in this case, we just change this, and the results would be 0 plus 0 is 0. 1 plus 1 is 2. 2 plus 2 is 4. 3 plus 3 is 6. And 4 plus 4 is 8. So it would be 0, 2, 4, 6, 8. Adding these together element-wise. So if I run this, 0, 2, 4, 6, 8. Now the subtraction is the same pattern, but this one would be way simpler since these are the same numbers, because it's 0 minus 0, 0. Oh, sorry, wrong spot. Hold on just a second. Okay. 0 minus 0 is 0. 1 minus 1 is 0. Notice the pattern. 2 minus 2 is 0. 3 minus 3 is 0. 4 minus 4 is 0. So if I subtract, then it's 0, 0, 0, 0, 0. Okay, that sounds like some kind of binary code or something. Okay, next is division if there weren't zeros in the denominator. But there's a 0, so it would cause a division error. If I run this, oh sorry, it's 0 divided by 0. Just if I started at, if it wasn't 0 divided by 0, it would cause a division error. If it was something else divided by 0, like, say, 3 divided by that. Oh, that didn't cause a division error either. In regular Python, it would. Like, watch. 3 divided by 0. See, 0 division error. So I guess PyTorch handles that by itself some way different. Okay, so next is, let's see, we did addition, subtraction, multiplication, and with the division, you can just exclude the 0 division, or the weird stuff about dividing by 0. Like this first thing, just forget it for now. But the other things, like 1 divided by 1 is 1, 2 divided by 2 is 1, 3 divided by 3 is 1, and 4 divided by 4 is 1. It's saying how many times will 4 go into 4? It'll go 1 time. 3 will go into 3 1 time. 2 will go into 2 1 time. 1 will go into 1 time. So that's why this is ones. Okay, so that's addition, subtraction, multiplication, division, now exponents. So the double star symbol is for exponents. So it would be this number raised to this power. Anything raised to the 0 power is 1, except possibly 0. I don't remember about that specific rule. Okay, next it would have 1 raised to the 1 power, so that would be 1. 2 raised to the 2 power would be 4, which is 2 times 2. 3 raised to the 3 power would be 3, 9, 27. It'd be 3 multiplied with itself 3 times. So, or 3, 9, 27. So this would be 27. And 4 to the 4th is 4 times 4 is 16. That times 4 is 64. That times 4 is 256. So this would be 256. Okay, now if I run this, 114, 27, 56. Oh, ignore that first one again. I guess it would be 1. So it would be 114, 27, 56. So I guess PyTorch counts 0 raised to the 0 power is 1 also. So I'll just put 1 here. There. Now it's accurate. All right. So that is how you do those. Now if I wanted to add another one, say copy, paste, call this C. The element, they have to be the same length. If I tried to add a length of 4 to these, it wouldn't work. The size of tensor A5 must match the size of tensor B4 at non-singleton dimension 0. So simplified version of what this is saying is tensor has a length of 5 and it must match tensor with which has a length of 4, or that tensor has a length of 4, and they must match the sizes, and they don't, so that's why it threw the error. So if I turn this to 5, there it goes. It all adds together. Let's see, grab this real quick, copy, change that to a plus, paste that down here. Okay, now if I add everything together, that would be 0s, 3, 6, 9, 12. 0, 3, 6, 9, 12. Okay, and same patterns for multiply, divide, exponents, etc. as before. Okay, so that's creating one-dimensional tensors, but you can also create two-dimensional tensors. It gets more complicated. I'm going to simplify it as much as possible. Okay, so have A. If I display that, it's 0, 1, 2, 3, 4. So I could put it in a list. That didn't work because it's trying to take a range of a list. But I could convert it to a tensor by typing, you guessed it, tensor. Yeah. Okay, now if I run it, there it is. There's the tensor. If I just put the number 5, it'll also convert to a tensor, but it doesn't have any brackets around it. So that would be, I believe that would be considered 0 dimensions, or a scalar, more specific. 0 dimensions and a scalar, I think, technically. So that would be 1 dimension. So I could try this out. 1, 2, 3. Okay, this probably won't work. Watch. Yep, type error. Tensor takes 1 positional argument, but 3 were given. So if I surround this in brackets, though, make it a list, then I pass the list, and there it converts it to a one-dimensional tensor. That's 1, 2, 3. Okay, now I can do something like grab this, copy, comma, drop down here, paste, and surround this with brackets. And now it's a two-dimensional tensor. Once I run it, it would show it's a two-dimensional tensor. Okay, so what this is doing is that's one row and that's another row. You could think of the dimensions as, 0 comes before 1. So you're walking along here, and then if it was a rock rolling, rock and roll. If it was a rock rolling off the edge of a mountain, it would drop down. So this is saying this one and so on. Or it's saying this is element 0 of dimension 0. This is element 1 of dimension 0, and so on. It's counting downward like this based on its brackets, its outer brackets or whatever. So the first set of brackets it sees, it groups this together. And then it's separated by a comma and so on, so it would drop down here. So that's probably kind of confusing. It took me a long time to really understand it. And so now, if I do like, let's see, 1, 2, 3, 1, 2, 3, I could put another one. I could do like this. And so that'll be another element. Whoops, hold on. Let's show this first. Okay, yeah, see that's a two-dimensional tensor. If I say dot shape, see it's 2 by 3. Remember I was saying the rock would fall down rolling off of a mountain right here, and it would go boop and drop down. So it would be, as it drops down, it would be like, okay, I see one row here, another row here, and if there's more rows, it'd be like another row, another row, another row. But this one, it only sees 2, and that's what this beginning thing is. The index locations start at 0, so this is dimension 0. Or sorry, this is section 0, whatever you call it. And then this one, what this is doing is as if it's going inside one of these rows, and it's counting the number of elements in there. 1, 2, 3 elements. So that's why it's 3 elements. And remember, they're supposed to be the same length too, because it wouldn't work to try to create something like this. It said expected sequence of length 3 at dimension 1 got 2. Yeah, dimensions was the right term, because dimension 0 would be the ball falling down and looking at how many things it sees. It would be falling in dimension 0. But if it's inside here, it would be like, how many things are in here? There's 3 of them, but it would be looking in dimension 1 to see if there's 3 things in there. So this says expected sequence of length 3 at dimension 1, but got 2. So there. Now if I run it, that works. Okay, now what I was going to show is copy, put a comma, enter, drop down, paste. Okay, so this one, now it's 3 by 3, because the ball falls down at dimension 0, and it sees one thing as it's falling, another thing, another thing. So it sees 3 things. And then when the ball goes inside one of the containers, it sees 3 things in there as well. So that's what this 3 is. So that's one way to think of it. And the things it sees first are called rows. Like that's a row, that's a row, that's a row. And then the columns you could think of as like columns that hold up buildings. They go up and down. So that 1, 1, 1, that's a column. 2, 2, 2, that's a column. 3, 3, 3, that's a column. So to remember what order it's in, it's the rows first, then columns. I use a picture like a RC car. It starts with R for rows, and then columns is next. So rows is dimension 0, columns is dimension 1. So that's the shape of that. And you can do mathematics on it as well. Like if I say mean and run it, oops, hold on, call the function. See what the error was. It said could not infer output D type or data type. Input data type must be either floating point or complex type. Oh, it's not automatically converting to floats. So I can do this, D type, zoom out so you can see it better. D type equals, I'll put torch dot float. I'll do float 32, just a random floating point thing. Okay, so if I was trying to be highly computationally efficient, like for putting it on a graphics card for AI processing or something, I would use probably a thing called bfloat16 if it was compatible, because that has more exponent bits than a regular float 16, but it still uses 16 total bits because it doesn't have to be as super precise down to extreme decimal places for the AI computations. So, but for this, I'll just do torch dot whatever it was before, float 32. Okay, now this should work for the mean. All right, it says 2 is the mean. Okay, so what is this doing? One way to find out, depending on the IDE you're using, is hover over and see the documents or the documentation inside there, see what it says. Okay. All right, dimensions. For the mean, you can add dimensions, keep them, and that, and data type. So what this means, dimensions, is saying if you're calculating the mean, well, just to simplify it, let's do the sum because it's simpler. So it's not trying to think of too many things at once. Okay, so the sum. So what this is doing is, by default, it's adding everything together. So 3 plus 3 plus 3 is 9. 10, 11, 12, 13, 14, 15, 16, 17, 18. So it's adding all of it together and saying 18. But if I put dimension is equal to 0, then it will do this. Okay, so it's adding this, this, and this together, like the ball's falling down, and it's saying, what's the first number I see? See is a 1. The next number I see as it's falling is a 1. Next number is a 1. Okay, it writes it down, climbs back up there, and then it drops down and says, what's the second number in each row that I see? It's 2, 2, 2. So add them together, that's 6. Then climbs up again, third number I see is 3, 3, 3. Add those together is 9. But if I put it at dimension 1, it'll be like the ball's going inside that row and saying, if I add all this together, what do I get? And then I'll go in here and see what it gets if it adds this together and finally this together. So 3 plus 3 is 6, or 1 plus 2 is 3, 3 plus 3 is 6. So each one of those should be 6 if I put dimension 1. Yep. Now, if I change this though, just if I change this to a 4, now guess what it'll do? Okay. So you can pause the video and guess. So what it'll do is, since it's dimension 1, it'll go inside the top container, add the stuff together. 1 plus 2 plus 3 is 6. Then it'll go to and it'll write it down. Then it'll go down to the next thing, add them together, write it down. Drop to the next thing, add it together, and write it down. So So this one's 6, this one's 6, but this one is 1 plus 2 is 3, plus 4 is 7. So that one's 7. So if I run it, 6, 6, 7. Okay. Now, 6, 7. All right. So now that you know how the dimension thing works, this other, notice inside this tensor, it's a single set of brackets around the values. But the keep dims, or keep dim, what that's saying is, see, by default it's false. It says keep dim equals false. But if I set it to true, what will happen? Can leave a comment, pause the video, leave a comment what do you think will happen. Okay, so what it will do is it will keep the number of brackets around it. Okay, so see how before it just had one set of brackets. In other words, one bracket on the left and one on the right. But the original thing had 2 brackets at the start and 2 brackets at the end. In other words, an open bracket and a closed bracket surrounding each of these things. So the keep dim equals true, it'll put an extra bracket over here and an extra bracket here. So if I run it, there it is. It rearranged the shape of it. I mean the looks of it, but see, now it has an opening bracket and a closing bracket that's surrounding the previous results. So if I go back to keep dim is false, run it, see, it doesn't have those extra opening bracket and extra closing bracket. Okay, so that's what the keep dims is. I'll just leave it at, well, actually I'll put it at true for now. Okay. And what else did it have? Keep dim. Okay, and then you can change that data type also if you want. All right, so that's the sum. Now I can do the mean. Follows the same pattern. So the mean, it's adding these together and dividing by how many things it added. So 1 plus 2 is 3, plus 3 is 6. And since it added 3 things together, it'd be 6 divided by 3 is 2. Same for here. But this one totals 7. So 7 divided by 3 comes out to be 2.33. Because notice I added 1 extra. So instead of 6, it came out to 7. And so since it's being divided by 3, that's 7. In other words, it has 1 extra. So if you divide that 1 extra by 3, that's 0.33. So now you can just add that 0.33 to the previous answer, and it gets 2.33, or repeating. So that's one way to conceptualize how that works. Okay, now you can calculate the standard deviation, which is 1.52, and the median, which in this case, it would be, since it's going side by side, the median of this row would be the middle number. The medians, if you organize the numbers from lowest to highest and pick out the middle number. So the middle number is 2. So the median would be 2, 2, and 2. Let's see. Yeah, 2, 2, and 2. Indices, yeah, that's the value. The indices, for some reason, it's showing the index locations as well, or maybe, I don't know. I don't know what that last part is. Okay, so that's how you do the median. And the mode means, it starts out, MODE starts out, MO. And so I think of that as most often, like what number appears most often. And here it wouldn't be any specific number, MODE. Okay, so if I run it, it just says 1. It has this down here too. Hold on, I'm just going to remove this. Okay, that looks cleaner. All right, so values, I guess that's a default or something. But if I put repeating numbers like 2 in here, now watch. See, 2 appears most often. Because 2 appears twice in this row. And then these others, I guess it's just random. I guess it's just picking the lowest number or something. Let's see. The mode has okay. But anyway, main point is the mode figures up the most often, the MO. So what appears most often, like 2 and 2. So 2 appear the most often. That's why it says 2 here. Okay, so now there's a mean, median, mode, standard deviation. See if it has variance. So there's the variance. So the standard deviation is the square root of variance. So if I do, let's see how to do this. A dot SQ square root. Okay. And if I put this in there, let's see how to do this. Tensor base takes no arguments. Oh, but one was given. Oh, okay. That's what it's doing. All right. So I can do dot sqrt. I think this will work. Okay, now call the function. There we go. All right, so that's 0.55, 1, and 1.5. So let's see if that matches with the the A dot, what was that? A dot standard deviation dimension 1. Okay, see if that matches. All right, so I'll do like this to see. Just put a comma here, run it. Okay, this is 0.57, 1, 1.5. 0.57, 1, 1.5. So the standard deviation is the square root of the variance. So once you calculate variance, then you can take the square root of it and it's equal to the standard deviation. So that's why for the variance, I took the square root of it, it came out with these numbers, and the standard deviation came out with the same numbers. So that's how that works. And let's see what else. Okay, so you can go even more intense and throw in another dimension. So do something like this. Scoot it over so it looks nice and organized to clarify. Okay, now I can copy this bundle of stuff. Copy. Place a comma here, drop down, paste. Okay, so now there's 3 dimensions. There's, once again, you can picture the ball. Comes out the edge of the mountain and drops down, and it looks at the outer set of brackets. One way to conceptualize it, simplify it, I'm going to restructure the looks of it. So it'll be more intuitive. Okay. It's like that. Then scoot this over here. Do like this. And finally like this. Okay. So now the ball rolls off the mountain, and it looks at this first group of stuff. And it's like, okay, what do I see here? Or how many things do I see here? There's one thing. There's another thing. So dimension 0, length is 1. Okay, we can test and see if this comes out right. So it should say 1. Okay, next it goes inside that top row. Remember, it counted one row, another row. So it goes inside that top row, and it'll be like, okay, now what do I see in here? I see one thing, two things, three things, or sets of brackets. So that would mean that dimension 1 is 3, and down here it would be the same, because the dimensions have to line up, or they're supposed to line up. Okay, now the ball would be like, okay, now I'm going to go another set of brackets in for each thing. So it'd be like, okay, how many things are in here? There's 3 also. So 3. So the dimensions should be 1, 3, 3, and let's see if it's right. A dot shape, and run it. And I got it wrong, apparently. Oh, sorry. Yeah, I know why. I said 1, but it's actually 2, going by the logic I was talking about. Yeah, so 2, 3, 3. Because what I was saying, like, the ball rolls down here, and it sees this. It's like, okay, there's one thing. It drops down again. Okay, there's another thing, so that's 2 things. I don't know why I wrote 1. But anyway, it's 2, 3, 3. Those are the dimensions. Or those are the shapes in the dimensions. Dimensioned, you can think of it as index location in the shape as the dimension. So index location 0 is dimension 0 in the shape. So you have 2. So that's the size of dimension 0. And then dimension index 1 of the shape, size is 3, and dimension index 2, dimension, which is dimension 2 inside the shape, size 3 also. So it's 2 rows, and then number of things inside that, each of those is 3 things inside of that, and inside of that. Then inside the innermost part is 3 things. So that's where the 2, 3, 3 comes from. Okay. And it can also initialize, instead of just creating a tensor with values like that, can initialize with random values. This is used in AI quite a bit. So I'm going to comment this out, and I will go down here, make it a little bit cleaner. So I'll go down here and then do B is equal to torch dot randin, which stands for random normal distribution, like a bell curve. And then I can put in the shape. Just say if I had or I can put in the stuff that I want. Like, just say if I want something with the shape of 2 by 3, then I'd put in 2, 3. If I run it, then watch what happens. See, it's random numbers from the random standard normal distribution, and see, they're centered close to, they're not far from 0, in other words. So it's shape of 2 by 3. So the ball rolls off here, and it sees this, and then it sees this. So that's 2 things. And then it goes inside one of them, and it's 1, 2, 3. So it sees 3 things. Down here, it also sees 3 things. So that's where that 3 is. So this is telling it to make that shape. How this can apply in AI is if you have data that's coming in and you want to create random weights for it. Let's call that W. So if you have data coming in and you want the random weights that are the shape of that data, then you can do it like this. And just say if the data is, say if this is the data. Okay, so if I do like this, uncomment, Okay, this is the shape of 2 by 3 by 3. So we can do 2 by 3 by 3, and it'll do that. Or I could do this shape of A. Oh, sorry, A shape of A dot shape. There, that also created a 2 by 3 by 3. So if I say what's the shape of this, that's 2 by 3 by 3. So it's automatic that way. And the more automatic stuff, the less room for human error. So that's another thing you can do with that. The most used calculation in artificial intelligence, or what uses the most compute, is dot products. And you can do those. Well, matrix multiplication is batches of dot products. So a matrix is something that's 2 dimensions. The way this is with 3 dimensions, it would be considered batches, where it processes multiple matrices at the same time, like on a graphics card, because you want it to carry as much data that would fit in the virtual random access memory on the graphics card as you can, so that it can process it simultaneously, because it has a lot of CUDA cores. And each CUDA core is like having somebody that's really fast at relatively simple math. So just if a graphics card has 1,000 CUDA cores, it's like 1,000 people that are really fast at math. And by really fast, I mean extremely fast. Like a old graphics card that could probably be, I don't know, $200 to $400 now, like a 1080 Ti. I think that's about the price now. That can process over potentially up to 10 trillion calculations per second. It's specifically called teraflops, or trillions of calculation, or trillions of floating point operations per second. And that's what the T-flops means. So it can carry batches of matrices. But in this case, to simplify it, I'll just do this. See how to go back to here. Do this. Okay, so that's 1, 2. I'll simplify it even more. Okay, so that's just a single matrix. There. And this one is the shape of, see, the ball falls down and sees 1, 2, 3 things. So it's shape of 3. And then it goes inside one of the containers and it sees 3 things. And that one sees 3, that one sees 3. So 3. So it's 3 by 3. Okay. So now, just to show I got it right this time, unlike one of the previous times, A dot shape. Let's see, missed, comma. Now, yeah, A dot shape's 3 by 3. See, 3 by 3. Now, if I go down here, uncomment this and this, do this, I can see the shape of this. This should be 3 by 3 also. Yep. So now what I could do is the dot product that's used in AI a lot. So I can say A, or this is matrix multiplication, which is batches of dot products. A matrix multiply with W. If I run it, it should work, but watch. If I throw in another one, or make it simpler, just less, but it's a different shape. Now it's a 1, 2 by 3. So it's 2 by 3. Now watch what happens. This will become a 2 by 3 also, but it didn't work. It says mat1 and matrix 1 and matrix 2 shapes that said cannot be multiplied. 2 by 3 and 2 by 3. So what this is doing is, with the matrix operations, the way that it's structured is it would do like let's see, I'll print out W. So it would say, instead of just doing it element wise, what it would do is, seems unnecessarily complicated, but it basically flips the things, and then it takes flipping another thing to compensate for that flip, and so on. So, okay, watch. Dot capital T, and that transposes. Okay, now see this one. So the ball falls off. It counts 3 things as it goes down. So that's 3. It goes inside there. It counts 2 things. So this is 3 by 2. And remember, this one's 2 by 3. So since this one's a 3 by 2, do 3 by 2. Okay, now I want the inner dimensions to match so that I can then use that at symbol for matrix multiplication from earlier. So I'll show you what I mean again soon. Okay, so you have A, which is 2 by 3, and weight transpose, which is 3 by 2. So the 3 and the 3 match. So another way to put it is, if I scoot this down here, or copy it at least, and paste, see the inner dimensions, that's the inner dimension, that's the inner dimension, because they're not touching the outside edges. So the inner dimensions match. So this would work if I do it in this pattern. So this is 2 by 3, so the inner dimension's 3. So I want the A to go first, then matrix multiply with W, which is 3 by 2. So this would be 2 by 3, matrix multiplied with 3 by 2. A matrix multiplied with W transpose. So now if I run it, now it works. And this comes out with these values. So what would happen is the AI would process a bunch of stuff and so on, and when it learns, what it's actually doing is it's adjusting the weights. So the weights were the things that were the 3 by 2, so W. So it would actually adjust these numbers so that whenever it does matrix multiply with whatever comes in, like A is the incoming values, then it should go through like a filter, which is the weights, so that it pops out with the correct answer. And these weights, if there's billions or hundreds of billions and things like, I think ChatGPT has hundreds of billions or more maybe of weights. If you hear of a model with a certain number of parameters, that's mostly what it's talking about, is the weights. So this would be a 6 parameter model. There's another thing called a bias, but it doesn't typically count for a very high percentage of the total. So this is the weights, and so this would be a 6 parameter model in that case. And let's see what else. Okay, so there's something called a categorical cross-entropy loss function, and before that there's something called the softmax activation function. So the way that softmax works is it'll take the output value, just say if this was what it predicted was the output value. I'm just going to grab one of these though. Say C is equal to that. Okay. D is equal to C index 0. D, display it there. So I'm grabbing one of these. So I'm just going to create a new line so it doesn't keep randomly changing the numbers. All right, so now I have D. All right, so D. So I run it again and it doesn't change. All right, so what I could do is say it's trying to predict something. And the softmax, it would be like, it would take E, which is a number that's found in nature a lot and in continuous compound interest. So it's about 2.71828. So I can say that, see, 2.71828. So I can take E and raise it to the power of each of these values, D. More specifically, well, yeah, that's good enough. All right, so E to the value of this. So what was this again? Hold on. D. I'll start it over. Okay, 4 and that. All right, so now if I run it here, what this is doing is it's taking the number 4 and using that as the exponent for the 2.71828, which is represented by E. So to verify that, I can say torch.e raised to this number. Oh, sorry. Torch.e raised to this number should equal this number, approximately. If I run it, there you go. 131, 131. Okay, and then the other one, 4.5. So if I raise it to the E to the 4.5, that should be, wait, what did I do? Sorry. If I raise it to the 1.5, it should be equal to 4.5 as a result. Approximately. 4.48, approximately 4.5. So this and this pretty much match. So that's what that's doing. E raised to the power of the tensor D. And so with the softmax, what it'll do is it'll take the results of that and it'll add them together. So I can do something like, call it, it's a fraction, so I'll just put top and bottom. Top is equal to, oh, sorry, it's actually bottom. Bottom is equal to this, but it would be the sum of this, actually. So let's run this in parentheses, dot sum. Okay, now if I run it, say bottom, that's 136. Because remember before it came out to like 131 plus 5 approximately. So that's 136. So if it's multiple dimensions, then you do, or keeping dims equals true, etc., or based on however you structure the AI system, the neural net. So, excuse me. So you take the bottom, which is the sum of the results of all those. Okay, so what the top is top is equal to that. So, whoops. Okay, so top, come down here. Okay, these are the values from before. Remember the sum just added the 131 and 5 approximately. And that's what got the bottom result, the BTM. 131 and 5 is 136. So now if I run this, okay, so to make it make more sense, I'm just going to put the top on top. Yeah. And the bottom on the bottom. All right, now top divided by bottom. Boom. There you go. All right, so that's the softmax. So what this is doing, D is actually called logits. I don't remember why exactly, but it's, yeah. So it's taking E to the power of an individual logit, such as this one. The logits are the raw outputs of the neural net. So it's converting them into percentages, basically. So see, this is 96%. Rounded to 97. This one's 3%. So 96 or 97% plus 3% is 100%. So no matter how many numbers you had, they would still come out to 100%. So this is the neural network's prediction for the correct answer. And that is the softmax, and it's taking the 4.8. It's taking e to that power. Then below it, it's taking all of these results, or e to each of those results, like e to the 4.8, like writing that answer down. Then e to the 1.5, writing that answer down. And then it's adding together those two answers. And that goes in the bottom of the fraction. So it's like a regular percentage calculation. You add everything together, put that on the bottom of the fraction, then you pick whichever one of those pieces you want to see what percentage it is of the total, put that on the top, and that converts to the percentage. So it's saying that it's 97% sure that location 0, whatever that represents, is the correct answer. It hasn't been trained, so it's just randomly guessing currently. And you can tell if I run it again, see the percentage has changed a lot. Now it's predicting this is more likely. It's about 64%, and that one's 36%. So that's how the softmax works. And there's after that would be typically the loss, which depends on what type of loss you're calculating, but a common one is the categorical cross entropy loss, which simplifies to be the negative natural logarithm of the target output class value. And if you do it in batches, then you get the mean of those, and that becomes a single number, which is the loss, and then that's used to backpropagate with derivatives to calculate how to change those weights, the W's I showed from before that change, how to change these, and the biases if they're added to, how to change those, but mostly the weights. And that's what teaches the neural network. And once it's trained, then you can just put new information in, and it can use the weights that are already adjusted, and it doesn't change them up, the new information. It just multiplies by that stack of weights as a filter, and then the results pop out as a number, and that's converted into whatever unit system you want, such as if you want it to predict a new word, then like for a transformer like ChatGPT, then it would spit out a number. That number would go to sort of like a dictionary, and then it would be connected to a word, and then, or a token it's called, and it would print out that word as a new one. And there's a lot more to it with transformers, but stuff like this is used inside transformers, the internals of it. So that's how this works, and let me know what you'd like to see next, and leave comments if you have any questions. And thanks for watching, and check out some other videos. They're over subjects somewhat like this. Thanks for watching, and please click like and subscribe.